Lab Report 3 by Jack Palacio. So for the introduction, our purpose is to utilize GlowScript to model Newton's law of universal gravitation. For part 1, we had to find the mass of a black hole by analyzing a star's orbit around it, and part 2, we had to find the initial velocity of a spaceship while having to complete a figure 8 orbit around a planet and moon without crashing. For part 1, the system was the star, and the surroundings were the black hole and the entirety of space. And part 2, the system was the spaceship, and the surroundings were the moon, planet, star, and black hole. For the overview, an effort was made to create a figure 8 shaped orbit, however it's nearly impossible to do that. The models and principles I used for this experiment was Newton's second law of position update formula, the velocity update formula, parallel and perpendicular forces, and universal gravitation. So for the first one, which is the velocity update formula, it states it's the initial velocity plus acceleration times change in time. The position update formula is just the initial position plus average velocity times change in time. Then for here we have perpendicular and parallel forces, so it's just F net perpendicular plus F net parallel equals F net. And we can break this up into F net parallel, which states that P final minus P initial over change in time equals parallel. And then for perpendicular, it's just mv squared over r. And then we have universal gravitation, which is just the gravitational constant times the two masses over the distance squared. So for part 1, where we had to find the mass of the black hole, these are just the initial conditions. We have the gravitational constant, the mass of the star that was given to us, and the change in time, which is just a day, and then which is 86,400 seconds. And then we have down here the iteration, which is just time plus each day. So here we're just finding the momentum, which is just m times v. So we're just finding it for the initial momentum and final momentum. And then to find the change, we're just doing the final minus initial for both velocity and momentum. For dp over dt, it's just the change in momentum over the change in time. And that's just equal to F net. To find parallel, we use the equation that we had, and after finding all that, we just get this. So yeah, so for F net parallel, would just equal dp over dt parallel, and then to find perpendicular, since parallel plus perpendicular equals dp dt, we can just subtract parallel from dp dt to get perpendicular, which just equals F net. And then to find the mass of the black hole, we're just doing the F net times the position of the star squared over the constant times the mass of the star, which is basically just the universal gravitational constant, but just solving for the mass, one of the masses. The results for that experiment, it basically just makes an ellipse around the black hole. So for the part 2, where we had to do the figure 8 orbit, we have the initial conditions over here, mass of planet, these are all given to us, and then this is just a month in seconds. So then we had to find moon speed and moon velocity, which is all given to us. And then here for speed x and speed y, this is where we just guessed and checked. So onto the code. To find the distance, we just do the moon's position minus the planet's position. And then for the force, it's just the universal gravitational constant. And then for the ship to the moon, we just do the moon minus the ship's position, same thing. And then to add the F net, we just add these two forces. Basically, we're just doing the same thing over here, but for the ship. So we're finding the planet on the ship and then the moon on the ship, and then just adding the forces. To find the velocity, we're just using the velocity update equation, and then we're also just using the position update equation. So here was the result. As you can see, it's not really a figure 8 orbit. However, it is influenced by both of the orbits, so it was fine. For sources of error, we're assuming that there were no other forces acting on the spaceship, which is highly unlikely in real life. We were using guess and check to find a velocity for the spaceship, which is unreliable, and the simulation doesn't always perfectly represent reality. So for what if and what does it mean? If we wanted to predict the motion of the entire system, we would have to include all gravitational interactions between every mass. We didn't do it here. So stronger forces would be between the planet and black hole, and weaker forces would be between the ship and the moon. For what does it mean? Net force and the parallel perpendicular components are written the same as change in momentum, but are different. Net force measures the applied force, like how the sum of all of them change the system, while change in momentum measures how the motion changes, whether it's speed or direction. Basically, in other words, the forces are the cause, and the change in momentum measures its effects.